Did we talk about the rational root theorem last Friday? No? Yes, we did. The rational root theorem is a theorem. It's a mathematical law that basically gives you a way to narrow down the list of candidates for zeros to a polynomial function. Okay, because back in the days before computers and calculators, finding the roots of these polynomial functions was very important. And this gave you kind of some guidelines within the work. So what it says, remember, is if you have a polynomial of degree n written in descending order like this with integer coefficients, so that's kind of the exception, it's a very specific type of polynomial, then if the function happens to have rational roots, and of course, what's a rational number? It's a quotient of two what? What's that? Integers. So take any two integers and divide one by the other. As long as 0 is not in the denominator, you have a rational number. So like 5 halves, negative 2/3. In fact, all the rational numbers will include all the integer numbers, right? Because you can put it over 1. All right, so if they happen to have rational solutions, fractions are still relatively nice numbers back in the day, then they're going to be of the form P over Q, where P is a factor of the constant and Q is a factor of the leading coefficient. So you do have to be careful because when you're writing it in descending order, the constant is the last thing you write, but it's the first thing you put in the form, right? It's the numerator. And the coefficient, the leading coefficient, comes first in the equation, but it comes second from the denominator in your quotient. And then I showed you on Friday how we already kind of use the factor theorem when we try to factor polynomials like this pink one here. The leading coefficient was 1, and so that would be the easy one to factor. We looked for factors of 6 to help us factor, and that then by the factor theorem gave us the roots 2 and 3. And if you notice, both 2 and 3 are factors of 6, the constant, right? Because when the leading coefficient is 1, the only combinations then of P over Q are just the factors of P. So of the 1, 2, 3, 4 times 2, of the 8 possible solutions, rational solutions, two of them worked. They were both rational. Okay, so remember though that this is kind of important. The theorem itself does not guarantee that the polynomial is going to have rational solutions. It just says if it does, it's going to be of a certain form. So let's try it out on example 2. It says to find the rational roots of that cubic polynomial, and then it says to be sure to list all the possible distinct rational roots. Distinct possible rational roots. I'm going to abbreviate possible rational roots today as PRR. It's just a little bit easier to write possible rational roots. What does distinct mean? Smelly? Like, ooh, that's distinctive. Oof. Non-repeating, what'd you say?
Like easy to pick out.
Easy to pick out, yeah? How about different, individual? Like these up here, 2 and 3 are distinct because they are different, right? They're different. If you had a root of 2 and a root of 4 halves, would those be distinct roots? What is 4 halves? 2, right? So it's not a distinct root. In other words, they have to be individual numbers. So 1/2 and 2/4, that's maybe a better way to say it. 1/2 and 2/4 are the same number, aren't they? So those are not distinct. Okay, so if we want to narrow down the number of possible rational solutions that are distinct, we can use the rational root theorem to do so. So this would be what you're going to quiz over tomorrow. So here's the first step when you're listing the possible rational roots. You're going to go ahead off to the side here, and you're going to put P and Q. You're not going to put P divided by Q because you're going to be listing things. P goes on the top, Q goes on the bottom. So you're going to list them in rows much like you will have them in quotient form. What is your constant in this case? Your constant. 2, right. The very back is 2. So P becomes the factors of the constant, which are plus or minus 1 and plus or minus 2. Now you list plus and minus because an integer factor is what we're after. So negatives could work as well. And then Q, what is the leading coefficient? 1. So that's plus or minus 1. So now all you have to do to list the possible rational roots, I'm not going to say distinct yet, but underneath there we'll put P, R, R, colon, the possible rational roots. All you have to do now is take all the numbers in the top row and then divide them by the numbers in the bottom row. Now, one word about the plus or minus. Plus or minus 1 divided by plus or minus 1 is either plus or minus. So when you have a ratio of two plus or minuses, you just take one plus or minus because the number itself is either positive or negative. What is anything divided by 1, though? Itself. So when your leading coefficient is 1, just like we saw on Friday, the possible rational roots are really just the possible rational integers from the leading, or from the constant at the back, right? Plus or minus 1, plus or minus 2. Now, how many distinct possible rational roots do we have? Well, we have positive 1 and positive 2, but then everything's plus or minus, so you always got to double it, so 4, yeah. And that makes a really good multiple choice question. I can give you that polynomial and just say, how many distinct possible rational roots does this function have? And because it's possible, then the answer would be 4. So you have 4 distinct, I'll write out the word distinct, PRRs. You don't even need the dot anymore. PRRs we'll just say is an understood acronym now. Okay, so what that means then is if we happen to have rational roots, I only have to try 4 of them out. Are any of those 4 guaranteed to work? No. But if they don't work, then at least I know my solutions aren't rational, and then maybe they're irrational or imaginary, okay? So it still gives us some information. Now all we got to do is try them out. We're going to pretend like we have no technology to help us. We're just going to try them out. So which of those 4, plus or minus 1, plus or minus 2, do y'all want to try out first? Negative 2? Have you already tried it? Okay. Okay, f of negative 2. You're the guy on Jeopardy that on a fresh board starts with like the middle $500 category right in the middle, right? Instead of starting with the 100 and going down. I like it, though. Let's try f of negative 2. Now, help me out here because these are big numbers. Negative 2 cubed is negative 8. Okay, y'all remember that because I have a horrible short-term memory. So negative 2 cubed is, oh, I just did that. Negative 2 times negative 3, positive 6. So what was this one? Negative 8 plus 6 is negative 2. Wow, that's a lot to remember. And then negative 2 plus 2, you already knew that. 0. So what does that mean if f of negative 2 is 0? That means that x equals negative 2 is a what? It's an x-intercept on the graph. It's a root or a 0 of the polynomial. And that means that what is a factor? X plus 2, right? It's always x minus that number. I typically put them in parentheses to make it look more factorish. So if negative 2 is a root, then x minus negative 2 or x plus 2 is a factor. Now here's what our goal is going to be. Let me write this up here. It's good to have goals, right? Goal, or goal, singular. We want to get to a quadratic. That's our goal. We're starting with a cubic, and I want to get to a quadratic. The reason I want to get to a quadratic is because I know how to solve quadratics when they're equal to 0. I know how to find roots of quadratics. It's easy, right? We either factor it, or if there's no x term, we separate it. We can take the plus or minus square root. Or, if none of that works, at least we still have what tattooed there, Mr. Pierce? The quadratic formula. So if all else fails, we can at least use the quadratic formula. Now, in order to get to a quadratic in this case, because I start with a cubic, I just need to find one factor. And I already did, right? Then I can factor it out, and what's left should be a quadratic. So let's say I have the number 350. Is 7 a factor of 350? It is, right? I can write 350 then as 7 times what? 50. How'd you get 50? 7 times 5 is 35 times 10, right? So basically 350 divided by 7 gives you 50, right? So 50 times 7 should be 350. Well, that's what I want to do here. I want to write f of x then. I want to write f of x, which is a cubic polynomial. I want to write it as x plus 2 times something. But I don't know what that something is. Do you? We can find it, though, the exact same way kind of Lauren came up with 50. If I gave you a factor of 7 and you wanted to know what 350 was in terms of 7 times something, you would divide, right? 350 divided by 7. We can do the same thing. I'm going to take x cubed minus 3x plus 2, and I'm going to divide it by x plus 2. And that should give me the other factor, right? Let's try it out. Long division. So underneath here, we're going to put x cubed minus 3x. Oh, let's do something else here. Since we're doing division, let's put a placeholder for the x squared term that's missing, and then minus 3x plus 2. That's going to be your dividend, and on the outside, I'm going to put x plus 2. And I should get a remainder of 0 here because I know that negative 2 is a root, so x plus 2 is a factor. So long division of polynomials. Y'all did it in Algebra 2? Algebra 2? Deuce, piece, yeah. If not, here's how you do it. I'll show you again. It's pretty fun, actually. Once you have everything written in descending order, you look at the first term of the divisor and the first term of the dividend. And you see how many times that first term in the divisor goes into the dividend. In other words, x times what is x cubed? Or, here's another way to think about it. What is x cubed divided by x? X squared. So that goes up here in the first spot. Okay, if you're not sure, take your dividend and divide it by your divisor. We're just looking at the first terms. X cubed divided by x is x squared. Now here's what you do. Now you multiply from on top, and that's where you get the plus 2 involved. X squared times x is x cubed. At this point, those should be the same. And then x cubed times positive 2 is plus 2x squared. Now the next step in the division process is to subtract. So you have to change both signs. All right, so now when I subtract, 0 minus 2x squared is minus 2x squared. And then you can bring down everything else, minus 3x and plus 2. Bring everything else down. And you repeat the process. How many times does x now go into negative 2x squared? In other words, what is negative 2x squared divided by x? Negative 2x. Yeah, you can do that off to the side. Negative 2x then goes up here. And we do the exact same thing. Now we multiply. Negative 2x times x is negative 2x squared. Those should be the same. And then negative 2x times positive 2 is negative 4x. Now we're subtracting, so we change both signs. So plus, plus. You should get a 0 in the first column if you did the division right. And now we have 4 minus 3 is positive 1x, and you can bring down the plus 2. How many times does x plus 2 go into x plus 2? Once. Or you could say how many times does x go into x? What is x divided by x1? When you distribute, you get x plus 2. And of course, when you subtract, you get 0. Yay! We knew we were going to get 0 because Ryland picked out a perfect root to begin with by trial and error. It was a lucky guess. It happens sometimes. And so we know it factors out. So guess what? Now I know the other factor. I can get rid of that question mark and say, oh, f of x then is x plus 2 times the quotient x squared minus 2x plus 1. Yay! So that's exactly what we did. 350 divided by 7 was 50. So 350 equals 7 times 50. But is 7 times 50 the prime factorization of 350? Or does 50 itself factor some more? It factors some more. So now, once we get down to this good-looking quadratic, you good-looking thing, you, now we can factor it because we have experience doing that. So let me go ahead, since I'm done with the division process, let me go ahead and shrink wrap that and put it in a space bag and store it under the bed. I didn't want to do that. I want to use the scissors. There we go. It's going to go with the sweaters. Oh, okay, did I take that? Yeah, I will. Oh, dang it. Yeah, this is, yeah, hang on. I did. I can do it. Just got to cut right through the two. Got to slow. Oh, I took the, okay. This is like a game now. Like Flappy Bird. There we go. Okay, now I'll shrink it down. And notice you could do another big circle and you can keep shrinking it down. You can put it like in super space bags. Watch. And make a big old circle. Super space bags. Okay, it's like floating away in the galaxy. Oh, there it is. It's way over there. Let's see if we can go a little bit further. Okay, super space bag. All right. Okay, so now anyway, we got it down to a quadratic, which means, let's see. Does it factor? Does that quadratic factor? X minus 1 times X minus 1. So the whole thing factors into X plus 2 times X minus 1 squared. Nice. Now, if I want to find the zeros, I need to set it equal to 0, and I can now list the roots. So X equals negative 2, and it's a multiplicity of 1, and X equals 1, and it's a multiplicity of what? 2. Did I account for all of my solutions? It was a degree 3 polynomial, and I've got a double root, which counts as 2, and a single root, which counts as 1. 2 plus 1 is 3. So yeah, there they are. So the actual roots were negative 2 and 1. Notice negative 2 and positive 1, are those in our candidate list? Yes. So it turns out all the solutions were integers, which means they were rational. So if you would have tried all of those values, you would have eventually stumbled upon all 3 roots. Okay? Pretty neat. Now, that long division process, I shrunk it way down. It was kind of fun, right? But let's bring it back into existence. It also was kind of complicated, wasn't it? Kind of complicated looking? No? It has a lot of X's and stuff in there. But it did get me what I needed. There are 2 types of oil for your car. You have conventional oil, which you have to change every 3,000 miles or so. You can go a little bit longer. And then you have the engineered stuff, the synthetic oil, that is engineered to resist viscosity and thermal breakdown, and it lasts a little longer. You can change your oil every 10,000 miles or so. It costs a little bit more. So just like with division, you have conventional division, which is both fun and fun. But there's another way called synthetic division. Yeah. Now, unlike synthetic oil that lasts longer, synthetic division actually lasts shorter, which means that the process itself is shorter. It's more streamlined. It's actually, if this is fun and fun, then synthetic division would be 3 things: fun, fun, and fun. It would be more fun. Okay. Do y'all remember synthetic division? No. That's what most people said last period. Let's revisit synthetic division. I'll write it right here. Synthetic division. Synthetic division, I'll show you if we have time today, if not tomorrow. It's just an algorithm that someone discovered, and they kind of streamlined the process. And it actually comes from something called nested form, which is very useful in computer programming. Okay? Your calculators, when they evaluate numbers or functions at numbers, they actually use synthetic substitution. Because if you remember me over here trying to plug in a negative 2, you remember how hard that was? I had to like break it up into individual tasks, and I had to have y'all remember those terms, and then I had to add them all together. That's pretty arduous. So synthetic substitution, as you'll see, is going to be much easier. So here's how you do synthetic substitution. You do have to know a root, okay? Or you can use it to try and find roots. What you do is you take your coefficients of your dividend, which are the polynomial we're starting with. So just like I wrote them inside the division house here, I'm only going to use the coefficients though. And I do need to write them in descending order, and I do need a placeholder for any missing x term. So what's the coefficient of x cubed? It's 1, so we're going to put down a 1. We're going to put down a 1, kind of just arbitrarily in space. What's the coefficient of the next x term? 0. So leave a little bit of space and put a 0 right next to it. What's the next coefficient? -3. Leave a little space, write it next to it. And then the constant is 2. So you're just working with the coefficients in descending order. If anything is missing term-wise in descending order, including a constant, at the end, if the constant was gone, you have to put a 0 for the constant. You need a placeholder of 0 because that term is gone. Now draw a horizontal line underneath it, but leave room for some other numbers. Leave a space for another row. So here's the mechanics. Off to the left, you're going to put a test box, and underneath the 2, you're going to put a result box, like that. Okay, so this is just how I format it. You might have done it a different way. You got a test box on the left, and you got a result box on the bottom right. Okay, so here's what we do. When we do conventional division, we have to do it with the actual factor. So you chose, what did you choose, -2? Yeah, you chose -2 to begin with. I'm still impressed with that guess. -2 was the root, so x plus 2 was the factor. When you do synthetic division, you don't use the factor x plus 2 because we don't have any x's, right? We're just working with the coefficients. So you use the root itself. So -2 is going to go in the test box. You use the actual root, not the factor. Okay, now we've already plugged it in and we got out a 0, so that result box should be a 0. Now the result box is actually 2 things. It's pretty cool. It is not only the remainder, it's going to be the remainder when you divide by x plus 2, division by x plus 2. But it's also going to be g, is that our function's name? F, sorry, it's f. It's also going to be f of -2. It's the y value. So that's why you can call it synthetic substitution. What did we get when we plugged in a -2 up above? We got out a 0, okay? What do you get when you divide that polynomial by x plus 2? We got out a 0 above. So it's both the function value and the remainder. Pretty cool. Now here's how it works. Here's how you evaluate it. The first step is easy. You just let gravity do the work. You prime the pump. Anyone ever pumped water from a water well, like on an old farm or something? Sometimes it's hard to get it started. You almost have to pour water in there first to prime the pump, to get the air out, and then you create the vacuum seal. So dropping down that 1 is like priming the pump. Now the process can start. You're going to multiply along the bottom this -2 in the test slot times the 1, and then you're going to slide the result up in the next column. So it's -2 times 1, -2. Now you're going to add vertically. The columns get added. 0 plus -2 is -2. And then the process repeats. You multiply. -2 times -2 is +4. And then you add vertically. 4 plus -3 is +1. Again, -2 times +1 is -2. And you add vertically, and lo and behold, we get 0. Now, this is a much easier way for me to evaluate the function at -2, because I don't have to get y'all's help to remember -2 cubed is -8, and then I have to come back to you. Because if I do it this way, all I'm doing is I'm multiplying and adding, and multiplying and adding, and multiplying and adding, and I'm doing it to my previous result. I don't have to remember anything. It's a recursive process. You build upon the number as you go. It's a lot faster. And this is how your calculators, your TI-84s, are programmed to evaluate functions. So if you type this function in, this ugly looking quadratic, and you graphed it, and you went trace, and you punched in a 3 or a -2, it's not going to go -2 cubed and store it, -3 times -2. It's going to do it like this. It's going to do it synthetically. And even though it might be more steps, your calculator or your computer program is going to be less likely to crash because it's just doing multiplication and addition. And it's not doing any exponentiation. And it's not storing values. It's doing it recursively. So kind of neat. I'll show you where that comes from later on. But right now, what we're after is the quotient, right? And what was our quotient? It was 1x squared minus 2x plus 1. It was a 1x squared minus 2x plus 1. A 1, a -2, and a 1. Do those numbers show up anywhere in our synthetic process? Where? At the bottom. Look at that. 1, 1, -2, -2, 1, 1. Is that a coinky-dink? No, it's not a coinky-dink. These end up being the coefficients of what we call a depressed polynomial. Why do you think we call it a depressed polynomial? Because it's in a math class? No, depressed in this case means smushed, smaller. It is 1 degree smaller than the polynomial degree we started with. We started with a what? Cubic? We took out a linear factor of x to the first. So this should be degree what? 1 smaller than 3 is 2. These are the coefficients of your quadratic. So you can do synthetic division, 1x squared minus 2x plus 1. That's awesome. That's awesome. Now, let's keep going here, because what we're going to be doing is trying to find roots of like 9th degree polynomials, and our goal is to get down to a quadratic. I'm at a quadratic already, so I can factor it. But the other roots that are still out there, I've only tried out a -2. The other roots that are out there now should be factors of this quadratic. So if you notice, you could redo the rational root theorem. For the quadratic, the only candidates that are going to work are factors of 1 over factors of 1. Well, that's only what? Plus or minus 1. So you can kind of even narrow down the search even more. Look what we could do. I could keep going with my result. And let me do that. Let me shrink that down. On your depressed polynomial now, you can keep going with the division. Let's draw another horizontal line. And we'll put a test box out here. Let's go ahead and try -1. Okay, we know it works, so we know we're going to get a 0 in the result box. But work straight down. You let gravity go. You got 1, multiply, you get -1. Wait, what did... Oh, well, -1 doesn't work. Let me just keep trying. Yeah. We get +3. 3 plus 1 is 4. Does 4 equal 0? No, it doesn't. So it doesn't work. It's supposed to be +1. So you can actually use the synthetic division process to test values. Now when I bring down the 1 and I try out 1, I get a 1. I told you I had a bad short-term memory. I thought it was -1. We plug it in, we get 1. We get a -1. Plug in, you get a -1. What's 1 minus 1? 0. So here's 2 of our 3 roots. And we could do it again. What would be the third root? If this was a quadratic, 1x squared minus 2x plus 1, now 1 and -1 are the coefficients of your depressed polynomial, which should be degree 1, right? So this would be what x minus 1. If you get down to linear, that's super easy. Just set it equal to 0 and solve. But 1 was a double root, wasn't it? If it's a double root, it's going to work twice in the division process. So let's try it again. Bring down the 1, you get 1. 1 times 1 is 1. 1 minus 1 is 0. And there you go. When you get down to this very bottom line with just a single number, this right here, number is your leading coefficient. It kind of has the feel of the upside down birthday cake. And then these numbers right here, these are your roots. So you can get the prime factorization of the polynomial. Your polynomial f of x factors into 1 times x plus 2 times x minus 1 times x minus 1. Pretty neat. Well, because we'd already solved it. Remember, once you get down to a quadratic, 1x squared minus 2x plus 1, we know that factored into x minus 1, x minus 1. So we already knew the solutions. If you didn't know the solutions, like on the next one, we're going to play dumb, you could just try it out and see if it works. If you don't get 0, it's not a root. Okay? But that's the idea behind it. We're going to do synthetic division. All right, let's try it out on the next one here. We'll go a little bit faster now. Example 3. This is more like your quiz here. List the distinct possible rational roots of g of x. Okay, and then it says to use your calculator to decide. We're not going to do that, because that takes the fun out of it. All right, first things first. The function's name is g. It's in descending order, so I write my p and q. P is the factors of 6, so that's plus or minus 1, plus or minus 6. It's helpful to list your factors as pairs. 1 times 6 is 6. And then from the bottom number 1, go up to 2. Does 2 go into 6? Yep, so it's plus or minus 2 and plus or minus 3. The next number would be 3, which we already have. 3 times 2. And then once you get to 4, once you get past half the number, you're done. You don't have to keep searching. And then 2 is going to be plus or minus 1 and plus or minus 2. All right, so now let's go ahead and list the PRRs, the possible rational roots. And it's going to feel like the distributive property now. You're going to take all the numbers in the top and put them over the first number, which is 1. And so you get the same things, right? Plus or minus 1, plus or minus 6, plus or minus 2, plus or minus 3. But then you come back and take all of the numbers in the top over 2, right? So all of these over 1, and then all of those over 2. I'm going to list them on the row underneath there. So now I get plus or minus 1 over 2, plus or minus 6 over 2, plus or minus 2 over 2, and plus or minus 3 over 2. And if there were another number under Q, then I would do all of them over that number. So it kind of feels like the distributive process. Now, if you count all those up, you have 4 on the top, 4 on the bottom for a total of 8 times 2 because of the negatives. It would appear that you have 16 possible rational roots. But are all of them distinct? No. So here's where the distinct comes in. Some of them might be repeated. So if you simplify them now, look at the bottom row. 6 divided by 2 is also known as what? 3. Do we have it already up there above? Yeah, so you don't need to include them again. And 2/2 is also known as what? 1, which we already have up above. The 3/2 and the 1/2 are distinct. So actually now you have 4 in the top, 2 in the bottom, so 6 total positives and 6 total negatives for a total of what? 12. So that would make a great multiple choice question. We have 12 distinct PRRs. 12 distinct possible rational roots. Not 18. Not 16. Not 13. Okay, so what does that mean? That means that if I wanted to find the rational roots, I only have to try 12 numbers. And trying like a 5 would be pointless. Trying a 2/3 would be pointless, right? Because they're not on the candidate list. So that's a manageable task, right? I just try out 12, and then I'm done with my chores, and then I can go out and play. 12 is a much smaller candidate list than what? What's the alternative if I didn't have this theorem? Infinitely many, right? Sorry, can't play. Got infinitely many things to do. Here's like, I got 12, and then I'll be out. Now, are any of these 12 guaranteed to work? No. But if none of them work, then at least I know my solutions, if they're not rational, are either irrational or imaginary, okay? What? Yeah, but it's not the rational root theorem. It's just factors of the constant over factors of the leading coefficient. That's what the theorem says. Remember, when we were factoring quadratics, we only used the last number and the first number to get our pairings. Remember we did target sum, target product? So the other terms don't really matter in terms of the possible solutions. And it's the way that you expand polynomials. First, outer, inner, last. The first ones are important and the last ones are important. So yeah, 13 is a coefficient and so is 1. But it has nothing to do with the irrational root theorem. Okay? Now we got to try them out. So now we have to list our coefficients in descending order. So here's where all of them come into play. We're going to have a 2x cubed, a 1x squared, a negative 13x, and a 6. So now you write all your coefficients in descending order. None of them are missing, and they're all in descending order. Now leave a little bit of space here because now we're going to be doing trial and error. It says to use a calculator to narrow it down, but I don't want to because that spoils all the fun. Let's use beefy brown. Okay, so of the 12 possible rational solutions, Ms. Goals, pick one. Any one from the list. You got 12 from which to choose. 2. Okay. Was that just arbitrary? Okay. Let's try it. I'll put a 2 right there. We let gravity do the first step. We bring down the 2. 2 times 2 is 4. 4 plus 1 is 5. 5 times 2 is 10. And you add and you get negative 3. And you get negative 6. And you get 0. Did you knew that worked? You randomly picked it. Interesting. Some people just have luck, right? So, yeah, 2 actually works, but wow. I was at least hoping we'd get 1 that didn't work. Okay, keep in mind that 2 works, everyone. Keep in mind that 2 works. Maddie, pick someone else to pick another number. Someone that's less lucky. Negative 2. Okay, let's try negative 2. Okay, if I bring down the 2, I get negative 4. Add, you get negative 3. Multiply, you get positive 6. Add, you get negative 7. Multiply, you get 14. 6 plus 14 is 20. Is 20 equal to 0? No. So very good. Thank you, Miss Looney. That's exactly what I was hoping for. That means that negative 2 is not a root of this function, and x plus 2 is not a factor, right? Now, what do you think g of negative 2 is? 20, right? But notice we got it just by multiplying and adding. Let's see what we can get over here. Help me out. Let's see if we can get it by plugging into the original. Negative 2 cubed is negative 8 times 2 is what? Negative 16. Okay, Jenny, remember negative 16. Got it? Negative 16. Negative 2 squared is 4. Tate, remember 4. You got 4? Negative 2 times negative 13 is positive 26. You remember 26, Lauren. And then this one is 6. Bridget, remember 6. Okay? All right. Whew. All right, help me out. It was going to be tough. We'll go from left to right. What was your number? I forgot. Negative 16. What was your number? Negative 16 plus 4 is negative 12. Okay, so now we're at negative 12. Okay, what was your number? 26. Negative 12 plus 26 is what? Negative 12 plus 26 is 14. Okay, good. 14. 14 plus, what was your number? 6. 14 plus 6 is 20. Man, that was hard. That was a group effort. Look at the other way to do it. Bring over the 2. Negative 4, negative 3. 6, negative 7. 14 plus 6, 20. Boom, done. I don't have to remember anything. I can do it on my own, recursively. That's why it's called synthetic substitution. That's how your calculators are programmed. Pretty fun, huh? All right, so negative 2 does not work. X plus 2 is not a factor. We need to find at least what to get to a quadratic? Well, we're at a cubic, so we really only need what to get to a quadratic? 1, right? And you can keep trying them over and over, but Ms. Gold's already found one for us. So let's go back to the 2 then. I just wanted to look at one that didn't work. If it doesn't work, you can kind of keep a list over here of things that don't work. And right now, you're gonna be able to. 12 is a manageable number to try out. Or I might just have you list the possible ones and tell me how many are distinct. Oop, I messed that up. So negative 6, we do get 0. Okay, so here's what we know then. We know that this polynomial, 2x cubed plus x squared minus 13x plus 6, it factors into x minus 2 times 2x squared plus 5x minus 3, yeah? Because these right down here, these are the coefficients then of your quadratic. So 2x squared plus 5x and then a minus 3. So we're home free, really. Let's see if we can factor that. It should factor in the product of two binomials. So, Mr. Pierce, this is what I was telling you about. When we factor something like this, we never really take into account the 5 until the very end when we do the inner and outer. The factorization only depends upon the 2 and the 3. Now, 2 is prime, so it's got to be a 2x and a 1x. And 3 is prime, so it's got to be a 3 and a 1. And it needs to be a positive and a negative. I believe that's the factorization. 2x minus 1 and negative 3. X plus 3. So now if I set that equal to 0, I'm still working straight up for space, I get my 3 roots. X equals 2, x equals 1/2, and x equals negative 3. And we're done. So if we can get down to a quadratic, we've got it made. Now let's do one last thing. This factorization right here, it's considered the prime factorization because they're all linear. But remember the factor theorem? The factor theorem says if a is a root, then x minus a is a factor. Notice the middle term has a 2x there. So if we factored out the 2 and pulled it to the front, we would have x minus 2, and that factor would become x minus 1/2, and then x plus 3. So that's just another way to get the prime factorization of g. That one is in the factor theorem form. The other one is acceptable as a linear factorization as well. But now you could just look at right here, okay? X minus 1/2 means 1/2 is a root. Now here's what else I want to keep doing, just to kind of show you the process. Once we know that 2 is a factor of the cubic polynomial, then any roots that remain are going to be roots of the remaining depressed polynomial of degree 2, which now after the fact we have found. So let's try them out and see if they work. Trevor, you asked last time where I got the 2 1s. I got them from the result. So if we already know that 2 works and we've tried it, 1/2 and -3 should also work. So let's keep going. Let's do the 1/2 first. I'm going to keep going on the result. 1/2 right there. Notice you could redo the factor theorem if you wanted. The remaining factors are going to be factors of 3 over 2. Bring down the 2. 2 times 1/2 is 1. 5 plus 1 is 6. 6 times 1/2 is 3. -3 plus 3 is 0. So that's your return box. And so now this 2x plus 6 is your linear factor that's left. And of course you could set that equal to 0, but I want to go all the way to the end. What's the factor that we haven't used yet? -3. So let's go ahead and do -3 right here. Bring down the 2, and you get -6 plus 6 is 0. Now notice what I said earlier. I said this number down here at the bottom, that's your leading coefficient. And all the numbers along the side are your roots, or your zeros. So if you wanted to factor it from something like this, let's say I just gave you that, and I said write the polynomial whose upside-down birthday cake synthetic division work is shown here. G of x would equal what? 2 times x plus 3, x minus 1/2, x minus 2. So it's always x minus the roots, and then your leading coefficient is out in front. And that's exactly what we wrote right here. Exactly the same thing. So synthetic division is pretty neat. It's very organized, and there's no x's in there cluttering it up. All right. So what we're going to do tomorrow, I'm going to show you where the synthetic division comes from. I don't know if we have time today, but there's something called nested form. Actually, I think we do. We have 2 minutes. Let's take this polynomial real quick, because it's not going to take long. G of x equals 2x cubed plus x squared minus 13x plus 6. The way you get nested form is by grouping these together right here, the ones that have the x in it, and you factor out an x on the right-hand side. So notice all I did is I grouped the 3 terms together that had an x, and I factored the x out on the right-hand side, and now everything that's left has 1 fewer x's. And I'll do it again. Now inside there, I have 2 terms that just have an x. So I'm going to have open, open, and I'm going to factor an x out. So I get 2x plus 1. I'll factor the x out on the outside. And then I have everything else that's left. Then it's going to be minus 13 close times x plus 6. And notice this is nested form. Look what happens here on my very first division process. Look right here at the very top. When I plugged in a 2, I brought down the 2. What was the first thing I did? I did 2 times 2. Well, if you plug it in a nested form, your dear Aunt Sally says go in the innermost parentheses, right? What's 2 times 2? 4. And what does my nested form tell me to do then? Add 1. What did I do over here? 4 plus 1 is 5. And then I multiplied 2 times 5. Well, guess what I'm going to do over here? I got 5 times 2. And that gave me 10. So I slid it up here. 10 minus 13 is -3. Well, guess what I'm doing over here? I'm doing 10 minus 13. It's going to be -3. The nested form says then to multiply by 2. That's exactly what we did over here. 2 times -3 was -6. We added it to 6, and that's what I'm doing here. So the synthetic substitution and division process are just streamlined algorithms for nested form. And that's what computer programmers are interested in, because that's how machines can compute things very quickly. Multiply, add, multiply, add, multiply, add, multiply, add. All right, Blake Fane, get a head start. It's not much. Do you have an elevator key? No? Okay. Someone go with Blake. Make sure he doesn't fall down the stairs. If you want to donate your can to the cause, you may leave it on the rolly cart. And if you didn't bring a can today, bring one tomorrow to collect your information. And have a super fantastic, wonderful, awesome, great day. You're off to a great start.